Alrighty, welcome back to 353. So we kind of survived a midterm-ish. So grading should be done. Grading will be nice. Grading should be done by March 4th at the latest, the TAs tell me. So scan them in later today. Start grading. Doesn't look too bad initially, so although no one finished early, so kind of concerning. But today, we get to take a little bit of a cleanser and just talk about fun sockets. So sockets, thankfully, are not anything new, but they will set you up for, doing a networking course or a distributed course or just any course where you want to communicate between machines. So sockets, just another form of IPC. So when we had pipes and signals and shared memory, that all needed the processes to be on the same machine, but now, well, the processes can be running on different machines. So some web server running somewhere else in the world and your actual machine that is trying to connect to it. It is also another form of inter-process communication. Typically, when we use sockets, we do it over a network, but we can also do it locally as well, as we will see in today's example. So, thankfully, aside from the system calls used to set up sockets, they are just file descriptors like anything else. You can read bytes to it and write bytes, or read bytes from it and write bytes to it. So, unlike just like opening a file, which is just one system call and you get a file descriptor back, sockets have a little bit more setup. And if you are the server, so there's usually like a server and a client. So server is just something that is running, waiting for people to connect to it and usually provide some type of service. Again, a website is an example of that. You have to follow 4 steps. So these are all system calls. They have the usual C wrappers where if there's an error, they return -1, set error no, all that good stuff. So the system calls that you have to call in order are 1, you have to call the system call socket. That creates a socket for you and it returns a file descriptor. The next is bind. So we have to attach the socket to some location. So it can either be, it's basically just a name or a way to actually access that socket. So you can attach it to a file, you can attach it to like an IP address, you can attach it to an IPv6 address and other things. Then after it is attached to an address, you use a listen system call. That means you are ready to accept some connections if someone tries to connect to that name, and you can set like a queue limit, and the kernel is the thing that manages this queue of incoming connections. And in order to actually get a connection, you have to do an accept system call. So that's a blocking system call, and it blocks until there is an actual connection made, and then it returns a new file descriptor, and that file descriptor represents that connection. So the file descriptor you get from accept, you can do a read system call on it and read anything someone else sends to it, or do a write system call and send information across the socket, and it will go across a network. And we'll have code examples today as well. So clients, it's a bit easier. They only have 2 steps to make. So their first one, they do that same socket system call to create a socket. They get a file descriptor back. The only difference is they don't have to do all of the setup. They just need to connect to some name. So there's a connect system call that connects to some location. And after that, the socket file descriptor can be used to send and receive data. The connect will want to use the exact same name as the server used for bind. So they are actually connecting to the correct thing. So what does the system call look like that both have to use? Well, it has 3 arguments. 1 really isn't used. So there's like int domain, int type, int protocol. So domain is just like the general protocol, and it tells you what the name is you want to connect to. So the 3 main options for domain is AF Unix. So that's for local communication on the same physical machine. That means the name you're going to provide looks like a file name. And then the other ones are INET, so that's for IPv6, like normal IP addresses, like 1.1.1.1, something like that. And that will typically use your network interface. And then there's IPv6 because, well, IPv4 is 32-bit and everyone likes connecting everything to the internet now. So they ran out of IP addresses quite a while ago. So there's IPv6, which is just a 64-bit address, but works the same, just more bits to use for the address, and it will also use the network. So the type, there's usually two options, stream or datagram sockets, and in a networking course, you might have heard the term like TCP or UDP. So these things I'll show you, they just mean the same thing, they're just called a generic name. And then this third parameter protocol, pretty much it's always 0, mostly unused, and we will not use it either, but it is there just in case some new type of name comes along. So stream sockets, they use TCP, so all data sent by the client appears in the same order on the server and vice versa. So with stream, there's like a persistent connection between client and server because, well, networks are weird, especially if you get into the networking course. Just because you send data in a particular order does not actually mean the receiver is going to see it in the same order. So it could like route your data, I don't know, some of your data through, I don't know, hopefully not North Korea, but something like that. And then the other one, you know, gets actually routed through Toronto or something like that, and it's more direct, so it might not actually arrive in the same order. But TCP will take care of all that stuff for you, and even if it takes some weird indirect route, it's going to handle it for you, and it's going to appear that all the information arrives in the same order on both sides. So it's reliable, it forms a persistent connection, and if you lose the connection, you'll be notified of it. It'll say, oh, you've lost connection, and it'll be reliable, but it might be slow because, well, it has to do some sophisticated things, again, that you'll learn in a networking course to make sure that things actually arrive in the same order. So if it's hard to do things in the same order, well, that's what datagram sockets are. So datagram sockets use something like UDP, and that just allows you to send packets of information or send messages between the client and server. There's no persistent connection between them, so it's fast, but you might actually, if something gets received out of order, you will see it received out of order. You might not get them in the same order. It's not guaranteed to actually make it to the server, and there's no way to actually check, like there's no persistent connection. So you don't know if the client actually sent you information or not if you don't see it. So you don't know if it was lost in transit or if they just simply never sent it. And yeah, so like sockets, again, if you want to see that sockets are actually used, like if you had a VPN client or you had, you know, a web browser or anything and you S-traced it, guess what? They're going to use sockets because that's how they communicate with web servers or anything like that. And then, yeah, the question, why can't TCP just attach the sent time to each packet? So TCP will do something like that, and that's how it will know. UDP, well, UDP doesn't have a persistent connection, so it's going to be fast. Messages might be reordered or dropped. And typically, you'll use UDP if it's something where, like, the overhead of checking everything just isn't worth it. So if you're doing like a game or something like that, by the time, you know, you click your mouse and try and update some game state, well, if it gets lost, it's not going to get resent because the game state already changed and everything like that. So using TCP isn't going to do anything for your game. So you're going to use something like UDP when it doesn't make sense to resend anything. You want things to be as fast as possible, and you can't really do anything to recover. If you want to go ahead and be able to recover and all that, then you should just use TCP. So the bind system call, that kind of sets a socket, like binds a socket to an actual address. So it takes that socket as the first argument here, and then Well, it just takes a socket address. Because it's C, it just takes a pointer to a socket address structure, and then you have to tell it the length of it. And yeah, so for most web servers and everything like that, they're going to use TCP. So TCP generally for web servers, and UDP is generally for games or like streaming lectures or stuff like, or streaming video and stuff like that, because if a packet gets dropped, it's kind of whatever. So it just kind of depends what you actually need. So in here, there are 3 different socket address structures for different purposes. So it depends on that domain that you set in the socket system call. So there are 1 structure for each type of name. So for Unix ones, they're just socket address underscore un. Again, I don't know why the developers decided to shorten things to the nth degree. Socket address underscore Unix would have been just fine, but whatever. But for these, it's just going to be a path. So it's just going to be like a file name, and that will represent a socket. And we will see that in our example today. If you wanted to do like IPv6 and all of that, or IP, it would just be socket address underscore in instead of inet. Again, don't know why, but this would be an IPv4 address like 8.8.8.8, which would be a DNS server. And then you have socket address underscore in6 for the IPv6. And that's going to be an IP address that looks something like that, which generally you don't see IP addresses, but if you actually look at the system calls, if you go to like google.com or something like that, it's going to connect directly to an IP address. How you go from a name to an IP address, you'll cover that in a networking course, so we won't go over the details. But basically, there's just some service that has all the name to IP addresses mappings, and you can go ahead and just look up IP addresses. So if you know the IP address, you can just like create a socket to anything. So if you really want after this lecture, you can just create a socket, figure out an IP address of something that the university does not own, and just send random data to it and see what happens and see if it responds to you. So it might not. You can go ahead, you can try it out. So the listen system call, all it does is sets queue limits for incoming connections. So it takes that socket that you have bound to some name and then takes a backlog. And the backlog is basically the queue depth that the kernel will maintain. So it's just the limit. And if you pass it a 0, the kernel will manage the limit. It'll just take the default limit, and the kernel will go ahead and handle it for you. At any rate, it is the backlog that the kernel handles of incoming connections that just kind of pile up, waiting for your process to accept them. And if you do not accept them fast enough, they're just going to get kicked out of the queue. They're going to get dropped, and you're probably, if you're trying to connect to it, you'll get a message like connection refused or something like that. So the accept system call, so that blocks until there's a connection. So you takes as the first parameter that socket that you have binded to something and are now listening to, then optionally takes an address again. But if you're doing like a Unix socket or like a stream socket, it's optional. You don't have to set them again. So you can just set them to null and ignore them. And at the end of the day, after this file, or after the system call returns, you get a new file descriptor represented by this int here, and then you can do your read and write system calls as normal. But now when you write to it, you are sending data to whatever client just connected to you, and when you read from it, you are reading whatever they sent you. So you can see what they're doing, and this is going to be the basis for the web, like web servers or anything like that. So if you just have a client, there is just, oh, yeah.
So go back to the example that you gave, where we can just send random information. If there's like a socket, then we can send random information to an IP address.
Yep.
They have to have like an accept, right?
Yep.
Okay.
Yeah, so like the web server running somewhere would have an accept, you connect to it, they would accept your connection, and then like normally if it's part of a web browser, the web browser knows how to speak to it to get like a web page back. So it will like ask it nicely, please send me a web server, asking it in HTTP or whatever the protocol is, and then you'll get a website back and then your web browser will render it. But if you don't know how to speak to it and you just send it random bytes, who knows what you get back? Yeah.
How does the we get from accept the same thing as the socket?
Yeah, so the question, is the file descriptor we get from accept the same as the socket? And the answer is no. The file descriptor you get back from accept is a new file descriptor that represents that connection. So you can keep on calling it over and over again because while web servers will probably have like thousands and thousands of people connecting to it, so you need to handle each connection separately so you know who you're sending information to and who you're getting information from. And some other questions. Is a socket just a bigger pipe that connects between devices? Yeah, it kind of works the same way. So the kernel will kind of manage it the same way. The only difference is with a pipe, we didn't need to give it a name. We didn't need to do all the setup, but it had to be on the same machine, and we could only actually access the pipe if we forked, and then through sharing file descriptors, we could go ahead and both processes could use the pipe. With sockets, because it's just a name, they don't need to be related at all. In fact, with sockets, they can be running on completely different machines. As long as you know the name, you can connect to it, but after all of this setup, their file descriptor, same thing as anything else. And then other questions, if we receive too much data, will we run out of the buffer or you set up listen? Yeah, so if you just send too much data, like if your file's too big or you send too much data with system calls, you'll probably get an error at some point where it will just reject whatever you're doing. Like web servers would probably be built in to just have some limits. So if you send it, if you don't tell it you're like sending it a large file, if you just start sending it a gigabyte of data, probably it might listen to you for a while, and then after a while it'll be like, okay, I have no idea what this person is doing. I will just close this connection, and then you would just get errors if you try and send any more information from it because the server just denies it. And yeah, we'll see an example later, but first, let's see the last system call we need in the client. So the connect system call allows the client to connect to an address. So looks exactly like bind, but except this is just for the client to connect to some server that is actually accepting connections. So it gets the socket file descriptor as the first argument, and then that same structure as before. So the socket file descriptor, again, is a file descriptor returned from the socket system call, and everything needs to agree. So the client needs to use the same protocol and type as the server, and then the address to connect to looks exactly like bind, and they have to agree with each other, like you have to connect to the same address as the server is listening to in order to form a connection. And the only difference is for this system call, if it succeeds, then you can use the file descriptor you got back from socket directly, just like a normal file descriptor, and you can read and write data to it, and it will go to the server. So we can just go ahead and write a server now. So it will be a very, very silly server. So in our example, the server simply waits for connections and then sends the string hello there to every single client that connects to it, and then it just closes the connection and it's done with it. So like all of our examples, they're in your materials repository, which I'll update right after the lecture, and the relevant source files are just going to be a client and a server. So we're just going to use a local socket for demonstration. You could use IPv4 or v6 if you want. For this, because we're using a Unix socket, it looks like a file. So it's going to create a file just called example.sock in the current directory, and we're going to use that as our socket address. So our server will also use some signals to clean up and terminate from our infinite except loop. So let's go ahead and see what the example is. So this is the server. So in the server, first thing it will do, so this is in main, first thing it will do is do that socket system call. So we're saying the domain's Unix, so we're just going to use a file, and then we're just going to use a stream socket because, well, we may as well, we'll form a persistent connection, we'll make sure everything is in order, and for the protocol, we just have a 0. So again, we do what we always do, we check if we have an error, so these are the normal C wrappers, so if it returns -1, means there's an error, it set error no, so I just wrote, this error no exit wrapper, just to go ahead and give us an error message. So after that, because we're using Unix sockets, I need to use sock address that structure to define it. So one of the parameters it needs is as one of the fields, there's Sun family, because this is really old when Sun Microsystems existed, and I guess they were there first, so they got the name. And because, as we know with libraries now, once you put something out there, you are now never allowed to change it ever. So it is now called this, even though maybe Sun still exists. I don't even know if Sun still exists. May or may not still exist. So we have to give it the same domain as we gave the socket to set the Sun family. And then the only other field we set is the Sun path. And it's just a string that it's just an array of a fixed length. And we can go ahead and just copy the C string to it. So our socket path is just going to be the string example.sock. And we just do a string copy just to go ahead and copy all the information to it. And then after that, that's where we do the bind. So we bind the file descriptor we got back from the socket system call. We give it the address of this socket address structure, and then because it's C, we have to tell it what the length of that is, so it's just the size of that socket address. Then after that, we have to do the listen system call, so we just listen, we give it the parameter just 0 to say, I don't care, just do your default kernel, you're probably smarter than me, so go ahead and listen, we'll go ahead, check for errors. And then this is the main loop. So pretty much every single web server in existence will look like this. It'll just say while true, except. So while true, except. So this accepts on the socket. We don't need to use the address again. So this system call will block until someone actually connects to it. If someone actually connects to it, it returns and we get a new file descriptor back that represents that connection. So we'll go ahead, check for errors. And then we're just going to do a write system call using that file descriptor. So we have our message, hello there. We calculate the length of it. And because it's a C string, we have to add 1 for the null byte. Then we just do a write system call with that connection and just send the string hello there to it. Check that we didn't have an error. And then make sure that we actually wrote all of the data, just like everyone surely checks the return value printf to make sure that they wrote all the data. And then we just close that connection. So we just close that file descriptor. Boom, we're done with this connection. And then the loop just keeps on going over and over again, waiting for new connections. Now in the in the client, same idea, we just have a socket. So we create Unix, socket stream, everything the same. We do the exact same socket address. So it's going to be Unix again. We set the Sun family, set the Sun path, and the two paths are going to agree. So it's going to be example.sock. And then we do the connect instead of bind because this is the client. So, oh geez, okay, so we connect using that file descriptor we got back from socket, the address of the socket address structure, then the size of it, and then after that, we can now use this file descriptor. We are now connected to the server. So, in this case, we know that this is very like, this is using our assumptions that the server is just going to send us data, so all we're going to do is read. So we'll create a buffer that's the size of a page. Go ahead, do the read system call in a while loop, so we'll just read over and over and over again. So just keep reading all the data we can until it is 0 or below. Check if there's an error. If there's not an error, well then the file descriptor returns 0, meaning that, like for pipes, means no more data is possible. And then we'll just print off all the data we received and close. So now we can go ahead and run it. So right now, if I look at my directory, it's just a bunch of random files, and there's no sockets or anything like that. So now if I run the server, doesn't look like it's doing anything because, well, if we straced it, the server is currently in that accept system call, just waiting for someone to actually connect to it. And if I go ahead and look at the directory, now I can see there's this example.sock. Looks like a file, but it's just the name of the socket. And it is in this fancy magenta color. Look at me with fancy names. All right. So now I can run the client, and the client will just say, hey, it received hello world. So there was some inter-process communication there. So that hello world came from the server, sent it to the client, and I can, because it's in an infinite loop and it just does the same thing every time, I can just connect as many clients as I want because it's just sitting there waiting for someone to connect to it over and over and over again, and it's just sending information to it. So, and then yeah, question, can we try and connect to this server? And no, you can't, because the only way to access it is because it's a Unix one, it's a local socket. So the only way to access it is through this file. So if you can't access this file, you cannot access the socket. Too bad, you can't go ahead and use it. If I went ahead and bound it to like an IP address, like whatever my laptop's IP address is, well, you might be able to connect to it. It depends on U of T's network security and whether or not they allow you to do that. So again, you will learn about that in the networking course. So whether or not you can connect to it is a whole nother thing. But if we knew IP addresses, we could go ahead and connect to it. And so, and then yeah, another question, if I share this file, can we connect to it? And the answer to that is no, because it is not a real file. It's just something that exists. It's kind of like an empty shell of a file, and when we bind to it, that system call, the kernel is going to know that, oh, if someone is trying to access this file on your machine, it actually references the socket you have created, and someone else can't connect to it. It has to be on the same machine. This file, if we look at it, actually, well, it just gives a bunch of question marks because it is not real, it's just a name. So there's no way to actually share this file with you because in reality, it does not actually exist. So any other questions or any fun things you want me to do with this? Yeah. So the question is, what if a client connects while the server is still processing? So in this case, how I wrote it right now, like it just accepts, and then if someone else is waiting, they'll just get thrown onto the queue that the kernel's managed. So they'll just sit there waiting to connect until this process goes ahead and actually writes it out and then closes the connection and then does an accept system call again. So it's sitting there waiting, blocking until that the server goes ahead and actually calls accept. So you can imagine this is where that example came up, where using threads with web servers is probably a good idea, because I could, instead of just like waiting to accept the new connection until I'm done with the old one, what I could do is I could have my main thread just continually call accept, and then after it accepts a new connection, it can create a new thread and then give that new thread the file descriptor that represents the connection, and let that new thread solely handle that connection. And the main thread can go back to trying to accept the next connection. And this is basically how web servers work. So they would have the same thing, but the main thread would just do accept over and over again. For each connection, they would probably just create a thread, and then the thread does all that work. Yeah?
Does the ping command use sockets, or is it different?
So the question, does the ping command use sockets? And yes, it has to. So if you strace it, it'll use sockets because, well, everything has to use system calls. Sockets are the only way to use your network. So has to use that. Was there another question? Yeah.
Like when you fork,
Yep.
you can still have multiple programs, like processes writing to the same socket, and that's fine.
So yeah, if I fork, then I would have multiple processes using the same socket. And then if two of them are doing accept and a new connection comes in, you don't know which process is going to get it, but one of them will get it. It's a bit weird. It's a bit weird if you do that because then you don't know what process is actually accepting the connection, but it would work. But it would, like, all the rules of fork still apply. All right, any other questions or fun things I can do? So, first problem with this server is, oh, okay, well, how do I stop this server? Well, if I want to stop this server, I can, this is where you would actually use a signal for something useful. So this server has like that example.sock file open, and maybe I want to clean up that file when my server is actually done running. But I don't know when it's actually done running. It's sitting here just most of the time, sitting here blocked in this accept system call. So if I wanted to actually clean up this example.sock file, well, to actually shut down the server, I should probably just actually use a signal. So what I did is I registered the sig int and sig term signal. So I registered them to call handle signal, and in handle signal, that's where I close my socket and do any cleanup I need to do before I actually exit my process. So in this close socket function, all I do is I close the file descriptor that represents the socket, which I made a global variable, and then to remove or delete the name, there is a system call called unlink. So I do unlink socket path, and then that gets rid of this example.sock. So I go ahead and clean up everything I was using when I close my server. So if I go ahead now and switch back to the server and hit something like Control-C, so now my server is done. And if I look at my directory, boom, example.sock does not exist anymore. So if I go ahead and in my client, I try to connect to it, I'll get, oh, connect failed, no such file directory because, well, there's no one actually listening to that socket. If I go ahead and let's say I messed up and let's see, PID of server. So if I don't want it to clean up all the resources, well, I can be mean and say just kill -9 and say, screw you, I'm going to not let you terminate cleanly. I'm going to not let you clean up. Again, kill -9, kernel kills it immediately. It has no options. So if I do that, I just see it's killed, and I'll see example.sock is still there, but no one's actually listening to it, but the file does exist. So if I run the client now, it just says connection refused. So the file's there. It's a name that actually exists, but there's no socket currently bound to it. So I just get good old connection refused, which you've probably seen the same message if you tried to connect to a web server that was down, or if you tried to connect, I probably shouldn't make fun of Quarkus or anything like that, but you've probably seen this before. And yeah, so there's another comment. If we use a thread to handle them, they might not execute in the order that they arrive. That is true, but typically you don't care. So between clients, it doesn't matter. Yeah. can I unlink a network socket? So unlink is only for like file names and things like that, not network sockets. So if you had a network socket, it'd just be bound to some IP address. And if your process isn't running, it's not bound to it anymore. The kernel's going to know about that. All right, any other fun questions or weird things we can do? But hey, this is the internet. If you strace anything, it will use sockets. If it's using the internet, like you said, ping command, your web browser, Chrome, Firefox, as long as it's running on Linux or Mac OS, doesn't matter, it's going to use sockets. So this, but aside from the system calls used to set it up, as soon as we got a file descriptor, then nothing really changed, right? It's the same thing we've been learning, but you know, there's going to be some weird protocols and stuff to actually successfully talk to web servers, but at the end of the day, they're going to just use sockets. And then other questions, oh, we want to get in trouble, so can we make a lot of requests to the servers? Will that break it? So sure, you can do that. That's called a DDoS attack if you want. So denial of service, where you just connect to a server, you just send random stuff to it in order to break it. So sure, you can do that, but there's ways to get around that. So if you see that, you know, some silly person is just connecting 1,000 connections or millions of connections and just sending you random data, well, you probably will want to set up something that just blocks them, and then you just don't accept connections from them anymore. And then, you know, that's your networking course. You can do that at the network level where the kernel doesn't even have to see it. And it just is blocked for you before you ever get to see it. Lots of fun things you can do with that because, well, like these things are on the internet. They can go ahead and they can do whatever. But if you use SSH or anything like that, guess what? That use sockets. If you use literally anything, that probably use sockets. And that's, yeah, that would overload the kernel's queue. You would get that connection refused if the queue's exceeded. And essentially, that's the same thing as a web server going down. And then another question, can you send signals between client and server? And answer to that is no. So for signals, signals are still kind of a form of IPC, but you have to do the kill system call and you have to know the process ID. So it's just another way to do IPC, but you can't send signals across across computers unless, you know, you use sockets and then you like make a request to send a signal on that machine to another process or something like that. So you can build these things up to do all sorts of different things, but at the end of the day, you're just sending data across a socket. All right, any other fun things we can do with this? Or any other questions? And then, yeah, question, what's the difference between unlinking and closing a socket? So in this, closing the file descriptor that you get back from socket means I'm not accepting connections from it anymore. So you can't connect to it, you'd get connection refused. And then unlink is separate from the socket. Unlink is a system call that just gets rid of that example.sock name. And if you actually like strace, if you do like rm example.sock like that, so that's like remove that file, right? And you can use that on regular files. But guess what? There is actually no system call called rm. Rm just uses the unlink system call. So there's no actual thing as like deleting a file. There's only unlinking, which is just getting rid of that name in the directory. So if I did rm example.sock, that's the same thing as doing unlink example.sock, that system call. And we can see if that's true. So like I can strace it and I can see, okay, I got invalid argument. Oh, I can't remove it. Is it still there? Cool. All right. Thanks, RM. What about if I force the issue? Really remove it. There we go. Okay, let's set it up again. I guess we have weird permissions because of that. So pid server. All right, let's just make sure I'm not full of it so we can strace it now. So if we strace it, we'll see we got slightly different, but it's the unlink system call. It's just unlink at the current working directory. We just unlink example.sock. So that's what RM does. There's actually no system call that's called RM. And then what, another question? Yeah, I did. Yeah, so if we use threads to handle sockets, again, they might be in the same different order. That's okay. You don't really care about the order between clients, realistically. They're usually quite independent. And then another question, do you need to remove unlink something if you're using an IP instead of Linux? So if you use IP instead of local sockets, you don't need to use unlink. So unlink is just removing a file name. So if I use IP addresses, I don't have a file name. I don't have to unlink anything. All right, any other final fun questions? All right. So instead of read and write, there's also some slightly different system calls called send and receive, but basically they're the exact same thing as read and write, except they have some flags. So there's some ones that get into more networking courses. So there's message OOB. So that's receiving data out of band, which means something if you take a networking course. There's peek, which is just look at the data without actually reading it. So you just kind of look at the data, see what you need to do with it, and the next time you do a read system call, you'll actually reread the same data. And then there's this don't route, so send the data without routing packets. Why is that there? Well, that seems really silly. If I need to connect to something, the packets probably need to reach the destination. So it might look like it's kind of weird to have this don't route, but that is there because guess what? If you're implementing a router or something like that, well, you can't route because you are the router. So that's what that is for. So you just send data directly to the source without routing, and that's used typically to actually implement a router. Otherwise, you could get into like infinite loops of packets, and if you thought this course was bad for infinite loops, wait for networking. So except for message peek, you will never use these. And routing just means like if I'm sending packets, like say my laptop was actually running a server and you wanted to connect to it, well, your laptop doesn't magically directly connect to my laptop. Your laptop would at least talk to that access point on the wall, and then through that access point, it would go then probably to my laptop if it was being direct. So that is called a route. So in order for your laptop to get to my laptop, it has to jump through at least one hoop. If we're in the same room, if we're in different rooms, then your laptop would talk to that, which would then talk to some switch in some closet somewhere, which would then talk to some big router that however the university connects to the internet, which would connect to some backbone, which would connect to something closer to your house, which would connect to the cable provider, which would connect to something eventually your house, and that is how information would actually reach your house. Again, set up for a networking course. I don't teach the networking course, but they're generally lots of fun because you get to go over all of those details. I think the one here is actually quite good. So just to set it up, if you want to perform networking, relating it to operating systems, you do it through sockets. So they're IPC across physical machines. Basics are they need an address, local, which would be a file name or an IP address, two types, stream and datagram. So stream, everything's in order. It's a persistent connection, so you know if you lose the connection. Datagram just sends messages. You don't know if they'll be in the same order. You don't know if they get lost. You don't know anything. So if you're the server, you need to create a socket, bind it to an address, listen to it, and then accept connections, and you can accept multiple. And then if you're the client, you just create a socket, you connect to an address, and that's it. So I will be here for the last 5 minutes for anything else, but just remember, phone for you, we're all in this together.